Study Center. I'd like to welcome you to this presentation on God's handiwork. An opportunity to reflect on the incredible creative power and majesty of our God. We have a special guest who's going to make that presentation, Dr. Richard Montagna and Kate Holstead, the head of the Rivendell, will share a little bit more about his bio, but we're delighted to have Dr. Richard with us, and we're looking forward to hearing from him. But before we continue, let us pray. The Lord be with you. Amen. Let us pray. Heavenly Father, we thank you for who you are, that you're a great God, and that even though we cannot fully comprehend the majesty and the power and the glory of who you are, you have revealed yourself to us in the person of Jesus Christ, the Son of God. We thank you that he lives in us through your Holy Spirit, and we pray that you would bless our speaker, that you would anoint him as he shares with us the realities of your creative work in nature and what that means for us as human beings, as your people. We also pray, Lord, that you would bless everyone here that in their own personal walks with you, that they would be drawn closer to you, Lord, as a result of our time together, and that you would keep us mindful of your call on our lives and the needs of those around us. We thank you and we ask it in Jesus' name. Amen.
Good evening. I'm Kate Holstead. I am the head of Rivendell Study Center, and I'm just going to give you a little information about that in case some of you might not know. Rivendell Study Center is a classical Christian education study center. It meets 2 days a week here at St. Bart's, and it's serving the homeschool community of Western New York. We have almost 70 students, grades 1 through 12, that come for our classes with our highly qualified, amazing tutors for a rigorous program of studies in the classics with our history and our rich literature. And it's just this beautiful Christian environment, and I am so honored to be a part of it. Many of our students are here, some of our families. I'm just going to ask some of my students to wave their hands. I'm so glad that you're here. You're getting extra credit. So I wanted to take a couple announcements for Rivendell before I introduce our very, very special guest. So Rivendell is actually a nonprofit, and one of the things that we do is our curriculum is called Tapestry of Grace, and it is many of our subjects. We're studying the same period of time throughout the study center, grades 1 through 12. And so this year we are focused on the 20th century, and we've got this fabulous opportunity at the end of classes, right after Memorial Day. We're taking a family field trip to New York City. So I'm doing a shameless plug here. There's a flyer in the back, and one of our parents, Linda Lescalo. Linda, where are you? She's got a couple of flyers. We're doing a fundraiser for that to help defray the cost of taking 25 people to New York City. So it's at Panera on Monday night. And if you go to Panera on Sheridan and present this, the students going to New York City get 20% of the proceeds pre-tax. So that's really a very generous thing. The other thing is, and yes, it's another fundraiser, it's for the scholarship fund for students to be able to help, well, families to be able to defray the cost of tutoring fees, which is very, very reasonable, but homeschooling families are notoriously frugal, and we've got some really great, wonderful, large families going, so we're having our scholarship fund fundraiser, and we're very excited. It's a little different this year. Our multi-talented tutors, Mr. Napoli, who happens to be the senior pastor over at Amherst Baptist, is also a professional caterer. So they are preparing barbecue for Memorial Day. If you are not a barbecue chef like myself, they are preparing ribs, brisket, pulled pork, and it's all cooked and prepared, and we're selling it by the pound. You pick it up on Saturday, and then you can just put it out and enjoy your picnic and everything on Monday. So there's going to be information on that in the other room. And so I just want to thank you for letting me do that, because the more we get the word out, then the more things that Rivendell can do. It's very exciting that we have a speaker that is so amazingly talented, and just in the conversations that I've had with him, he's amazingly humble and such an amazing man of God. So let me read you his truncated bio to give him the credentials to be able to speak with authority on the subjects that he's talking tonight. Richard is Senior Vice President for Scientific and Clinical Affairs at Rheonix Incorporated, a company that develops human diagnostic tests. He has over 35 years experience in the biotechnology industry and has led the development of numerous biotech products, including FDA-approved diagnostic tests. He has been awarded more than $10 million in federal grant money to support his research, published over 45 scientific papers, and holds a number of U.S. patents. Richard earned a PhD in molecular biology from the University of Buffalo in 1975 and continued his education with postdoctoral training at both NYU Medical Center in New York City and the MD Anderson Cancer Institute in Houston, Texas. During an invited testimony before President Reagan's AIDS Commission in 1988, he recommended nationwide screening of the blood supply for the presence of a virus related to the AIDS virus. Mandatory screening of the U.S. blood supply was implemented soon thereafter. He held an adjunct professorship at Cornell University for 18 years, and in 2014 was inducted into the National Academy of Clinical Biochemistry. Finally, he is a frequently invited speaker at international scientific meetings, speaking primarily on the topics of molecular diagnostics and personalized medicine. Would you please welcome Dr. Richard Montagna.
After an introduction like that, the only direction I have is downhill. So I hope I can live up to expectations. My goal tonight is to talk to you from the perspective of a Christian scientist and what I see in the physical universe. It's how it points to God's glory and the absolute requirement of our Creator. And when I refer to myself as a Christian scientist, I don't mean I'm a member of the Church of Scientology. I'm a Christian that happens to be a scientist. And the way we're going to do this tonight is we're going to look outward first into the huge cosmos of space. And then we're going to look inward into the cosmos of our own human selves. Now, when we look outward, I'm not an astrophysicist, I'm not an astronomer, I'm not a cosmologist. I read a lot. And that's what you're going to get the benefit of what I've read. On the other hand, when we turn our attention inward, I'll be talking to you about what I've seen with my own eyes and what I've done with my own hands. When I look at this scripture, it just reminds me that the psalmist got it right. Also reminds me that as a scientist, I feel like I have this privileged front row seat to see aspects of God's creation that most people don't ever get to see. Now, I got a point back there? Very frequently, when anyone wants to talk about their faith or want to talk about the relationship of science and Scripture, people always want to know about the conflict. And I'm going to tell you right from the outset, we're not going to spend a lot of time in it, and the reason we're not is I believe that, well, first of all, I should state that probably one of the biggest elephants in a room in a setting like this is evolution versus creation. And if it's not that, it's are we standing on a 6,000-year-old planet, or are we standing on a 3.7 billion-year-old planet? In my mind, I can't subtract God away from the creative act. So for me personally, it doesn't matter how these get resolved. Because my faith is based on Christ and His resurrection. So how this gets worked out, I actually don't care. I also believe that if you could take all of science and put it in one book, so I'm talking chemistry, biochemistry, biology, my field, molecular biology, which, by the way, is just the study of DNA, geology, astronomy, physics, astrophysics, quantum physics. I believe the author of that book would be the same as the author of the book of Scripture. So at some point in time, we'll see that they can be reconciled. But I also think that you can stratify people based on their worldview. Now let's say over here, I guess this is your left, we've got people who are very secular in their beliefs, and they discount God from everything. As far as they're concerned, God doesn't exist. And over here, you've got people, hopefully like most of us, that believe that not only is there a God, but He's the Creator. And you've got everybody in between. Well, there's the people on the very ends will probably find virtually nothing to agree to. People somewhere in the middle maybe have some common ground. But regardless of where they are, I think there's one thing they will all agree to. And that is somehow, something came from nothing. Everybody agrees to that. And in fact, if you think about it for more than 2 seconds, everything came from nothing. So we're going to spend some time talking about that. Now, first I want to talk to you about 3 scientists and their views on God. And I'm going to start with one that you might think is surprising. Apparently I have to point back that way. Probably one of the most recognized faces in all of science. And most people would probably think Albert Einstein was an atheist. He actually was not. Because of the complexity that he saw in the physical universe, he believed there was a necessity for a creator. So if anything, he was an agnostic. Kind of believing God set everything in motion and then now just sits back. But as he gained notoriety, people continually asked him what his view on God was. Now, in order to appreciate why people even asked him, because they viewed him, obviously his name is synonymous with genius. And they also recognized that he understood the complexity of the entire physical universe, not only from the cosmos of space, but down to the smallest of quantum particles. And in order to appreciate what he really knew, I'm going to take us back over 100 years. That's the 26-year-old Albert Einstein. And I picked 1905 because if you are a student of Albert Einstein, you'll know why I picked it. It was referred to as his annus mirabilis, his miracle year. Because in that year, he published 4 groundbreaking papers that turned the world upside down. And in the world of science, we call groundbreaking papers seminal papers. And any scientist would love to have one seminal paper in their entire life. He had 4 in 1 year. And it was before he even began his career as a university professor. At the time, he couldn't even get a job at a university. At the time, he was a patent examiner, 3rd class, in the Swiss Patent Office in Bern, Switzerland. So these 4 papers he published in his spare time. Can't imagine what he would have done if he had more time. We're not going to go through the specifics of the papers, but I want to give you an idea of just how brilliant he was. Because when we start talking about his views on God, I think it'll help. His first paper was on something called the photoelectric effect. We're not going to go into a lot of details, but basically if you shine light on a metal, it'll eject electrons. And people struggled with how that even happened. And he came back and said, light exists not only as a wave function, but in discrete packets of energy he called quanta. We call photons. Not everybody agreed. People tried to disprove him, and many people tried to disprove him. 16 years later, in 1921, he was awarded the Nobel Prize for that work. So he was bright. Then, I'm sorry, I keep pointing out. He was actually able to prove that atoms actually exist. Up until then, nobody really knew for sure. And again, we won't go into details. It's actually quite a simple experiment, but he proved it. The third paper described the relationship between energy and mass, and they both can be interconverted. Gave rise to probably the most famous equation in all of science, E equals mc squared. And then finally, the paper that, now all this stuff is going on, and scientists are all talking among themselves, but the lay people, they didn't have quite as they do who Albert Einstein was. So he came out with this theory of relativity, which in its simplest form simply states the flow of time is related to how fast you're moving. If you move slow, if you're moving very, very fast, time moves slower. Sounds very bizarre, but it's true. Well, he realized when he published that paper in 1905 that it only worked under very special conditions. Only worked when the observer was moving at a constant rate of speed. If the observer was accelerating, the equations didn't work anymore. It took him 10 years to revise his theory, and he published the second paper in 1915. And he called that paper the general theory of relativity. This paper became known as the special theory, because it only worked under special conditions. Well, the special theory had all kinds of bizarre things. It really shook the scientific community because all of a sudden some of Sir Isaac Newton's thoughts on gravity had to be rethought. And then he also predicted that the sun could actually bend light. The gravity of the sun could make light bend. People thought he was really nuts. And if you think about it, if we went outside tonight and looked at the stars and saw where they were, if you go back tomorrow, of course it's not dark out right now, but if it was, the stars are still there, but you can't see them because the sun is so bright. But if you could, they wouldn't be where they appeared the night before. They would have looked like they shifted over. And to give you an idea of what I'm talking about, this is where the star would be at night. Now, in the daytime, with the sun there, the gravity of the sun would pull that light around, and if you were standing on the earth, and if you could see it, which you couldn't, because it's too bright out, the appearance of the star would be shifted. I have an Italian nose that likes to run. But he also said, there's a huge cosmic experiment that'll fix this. It's called the solar eclipse. And, we had one here last year, but it wasn't total. We didn't experience totality here. Had we, the stars would have reappeared at night or in the daytime. So he also predicted that, this isn't really bright, so anyway, you see the little arrow I put up there, that's the angle. He actually predicted that angle. And then in 1914, he said, he arranged to have an expedition go to Crimea to measure the shift in the stars as a result of the solar eclipse. Unfortunately, World War I started, and the people that were in Crimea were actually arrested by the Russians as spies. They've got all this equipment out there, and what are you guys doing? They're German, so that the experiment never took place. But in 1919, another solar eclipse took place, and this photograph is a very famous picture. That picture was taken in 1919 by Sir Arthur Eddington. It's actually two pictures. He took pictures at night, Then he took a picture during the solar eclipse, and he laid the two photographic plates on top of each other. And what you're seeing, see those two arrows? Those are the stars where they were at night. And the reason they appear as a streak is the shutter is left open and the Earth is moving, so you get a streak. And you got two streaks. During the eclipse, that's where the stars were. Not only did they shift, they shifted by the exact angle he had predicted. So all of a sudden, Arthur Eddington, who's now off the coast of Africa, is going to get back on a boat and get to London. It took him many months to get back, and 6 months later, on November 6, 1919, he presented this data to the Royal Society. The very next day, these headlines appeared. The one on the left was in the New York Times. The one on the right was in the London Times. All of a sudden, Albert Einstein was a rock star. Everybody wanted to talk to him. Ultimately, he ended up in the United States. He fled Nazi Germany in 1933. By the way, I read an interesting book called Einstein in Berlin. He created quite a dilemma for Adolf Hitler. Hitler loved Einstein because he was a world-famous scientist and he was German. But he hated him because he was a world-famous scientist and he was Jewish. So Einstein came to the U.S., started out at Caltech, ultimately was recruited to Princeton, where he lived out the rest of his life. So let's go back to the grandfather, Albert Einstein, that everybody asked him about his views on religion. And he said, it's really a hard question to answer. Because unlike things in a laboratory, in science, where you can test it in a laboratory, you can't test for the existence of God, but you can infer it. And he proposed what he called a thought experiment. And Einstein was very famous for thought experiments. All his relativity work was not done in a laboratory. It was done sitting in his office thinking about the most bizarre things. So he proposed a thought experiment. I'm going to give it to you. Let's assume we walk into a large metropolitan library. It's got thousands of books written in multiple languages, and you're asked, where did it come from? And you're given two answers. One, it just appeared. Wasn't here yesterday, but it's here now. That's the first answer. Second answer is somebody wrote the books. Somebody printed the books. Somebody bound the books. Somebody stacked the books. And while you're at it, somebody designed and built a library. Which of those two options do you pick? And he said, obviously, you pick the second one. Because the library is too complex for it to just appear. And then he said, the library is nothing compared to the physical universe. So how can we say there's no designer? That's actually his thoughts. And then a year before he died, this was a very famous quote. It's one I actually subscribe to. You have to understand both. Now, although he did not believe in a personal God, but I do want to expose you to two other scientists that do. Both are Christian. I don't know if you know who this person is. This is Francis Collins. He is the director of the largest research institution on the planet, the National Institutes of Health. This picture actually doesn't do it much justice. It's about a third of it. There's a third on either side. It's a 300-acre campus. It's got 27 institutes. They got a budget of almost $40 billion a year. The building in the front is the administrative office. The building right behind it. When you're on the I spent a fair amount of time on that campus. The building in the back there is called Building 10 to the people who are on the campus, but to everybody else, it's the National Cancer Institute. So that's it. To be a director, you have to be appointed by the president. He was appointed in 2009 by Barack Obama, appointed 4 years later, Obama's second term, and appointed again by Trump. So he will be into his 12 years of serving. And people were really concerned in the scientific community because he's a very outspoken Christian. And they were afraid of what he would bring to the table. And he's written a number of books. I've read all of these. I actually like the one on the far left, The Language of God, because it talks about DNA. It's a really well-written books, and if you like that sort of thing, I would encourage you. And I want to expose you to one more scientist. I would be remiss if I didn't talk about this person in an Anglican church. If you don't know who this is John Polkinghorne, a very world-famous theoretical physicist. KBE, after his name, means Knight of the British Empire. He was knighted by Queen Elizabeth in 1996. And he refers to himself as a cradle-Christian. He was brought up in an Anglican home, and he also has written, I think right now he's up to about 27 books in terms of the relationship between science and religion. And here's a quote from one of his books, Science and the Trinity, where he affirms his faith in Christ and where he comes from. But in 1979, he shocked the scientific community because it was time for a career change. And it's depicted in this book, Quantum Leap. Also, I read this book. It's a great book. Quantum Leap was an appropriate name because he was a quantum physicist. But the leap was that he became an Anglican priest. And he continues to be. I think he's like 87 years old right now. Prolifically writes and tries to reconcile science and religion. So there's the background. And I think it shows that if you have Christian beliefs, it does not mean you have to check your brain at the door. I would challenge anyone to talk to any of these guys. And he's written a number of books. I couldn't fit them all on the screen, otherwise you wouldn't see them. You saw 27 of them. All right. Let's look outward first. One of the things that you have to grapple with is, all right, so however creation came into existence, what was there before that? What was before time? You know, people who accept the Big Bang Theory assert that time began with that instant, with that so-called singularity, with that first burst of energy that turned into everything. But what was before that? And really what it's doing is it's merging the fields of theoretical physics and religion. If you read, I don't read a lot about theoretical physicists. It's, to be honest with you, a lot of it's like way over my head. But it's, you almost feel like you're reading a theologian because of the way they have to describe all of this stuff. But you have to ask yourself the question, if something came from nothing, what is nothing? Is nothing just a big vacuum? And if that's what it is, that's still something. So I actually I don't know that anyone's ever really truly answered what is nothing. And what came before that? And then, of course, who caused something to come from nothing? Who or what? If you're the secularist, you say what? If you're a theist, you say who? But somehow something came from nothing. And I think, to me as a Christian, the only answer is something, someone that's outside of that whole thing. And I think the answer can be found in Exodus. When Moses is being told by God to lead the Israelites out, remember what he said? When he said to God, who am I going to tell who's sending me? He didn't say, the I am that came into existence, the I am that had to be hidden. Sorry. The I am that I am. That's who did it. So, it reminds me of a story, actually. This is make-believe, obviously. World-famous scientist confronts God and says, we don't need you anymore. We figured out all your secrets. In fact, and he swipes his hand across the table, like you, I can take this dust and I can turn it into life. And God looks at him and smiles and says, show me. So the scientist says, okay, watch this. And God says, wait, smiles even broader, knocks the dust out of his hand and says, first, get your own dust. And that's true. Think about it. Something had to come from nothing. Well, here's our Milky Way. That's where we are, way out there. That's not us, that's our sun. Before Edwin Hubble in the early, about 1920s, everybody believed that that was the universe. But Hubble, with his 100-inch telescope out in California, was seeing things that he realized weren't stars. There were other galaxies beyond our Milky Way. And if you look, the width across that is about 100 to 150,000 light years. It's actually a small galaxy. Some galaxies are millions of light years across. And if any of you have read Hugh Ross, Dr. Hugh Ross, a Christian astrophysicist, he refers to that location as the Goldilocks zone. We're in the right place. If we are any closer in, there would be too much cosmic radiation for life to exist. And also, we wouldn't see anything because it would be so bright. So we're kind of out here in the darkness, far enough away from the cosmic energy of the central part of the galaxy, but also we can see the majesty outside. Well, turn the clock up to about 1990, and Hubble was recognized by naming this space telescope, the Hubble Space Telescope. It's orbiting, it's been up there since 1990. I'll give you an idea, it's about the size of a school bus, and it's got a pointing accuracy of 0.007 arc seconds. What does that mean? If you took a circle and divided it into 360 degrees, then you took one of those degrees and you divided it up into 60 little sections, those are called arc minutes. If you took one of those arc minutes and divided it again by 60 more pieces, that's 60 arc seconds. So it's got a pointing accuracy of 7 thousandths of an arc second, and its ability to observe objects is 500ths arc second. So in order to try to drive it home, I might need a little volunteer, and maybe one of the students, if anyone's, I won't embarrass anybody, if anyone's, no volunteers? No? Okay, come on. This is a Roosevelt dime. So what I need you to do, I need you to hold it like that, off to the side. The problem is, you have to get in the car and you have to drive 200 miles away. So the best we can do is go to the back of the church. Now, if he was 200 miles away, and I'm Hubble, and I don't know, this hasn't been very bright, I should be able to hit the cheek of that coin. Okay, you can keep the time. So, if that was 200 miles away, Hubble could do that. It shows you how accurate it is. Now, as far as its ability to resolve images, this is a pair of fireflies, mating fireflies. And you know how big a firefly is. It's tiny. It obviously is a magnified picture. If I wanted to volunteer for this experiment, I'd have to send you to Buffalo Airport so you could fly to Tokyo, Japan. Hubble can see that. So that's its capability. So, if you took a grain of sand, stuck it on your finger, held it way out, that's the amount of sky that Hubble sees when it takes its pictures. And this is a very famous picture. you look at this picture, you are not seeing stars. You are seeing galaxies. And in that picture, you have to count them, but there's 10,000 galaxies. Every one of those galaxies is estimated to have 100 billion stars. And it is assumed that the observable universe has 100 billion galaxies. Add all that up, 10,000 million stars, or 10 to the 22 for people like me. It's easier that way. That's how many stars are in the observable universe. We don't know what's beyond it, because we can't see it. Well, the observable universe, from our perspective, is about 46.5 billion light years in all directions. Now, that doesn't mean that we're in the center of the universe, because frankly, we don't know where we are. We just know that we can see 46.5 billion in all directions. So I'm going to show you a little home movie. My wife and I love it. My wife's here actually tonight. Donna's here, and one of our daughters, Leanne. We both like to cruise, but I think I like to cruise more than she does. Because I like to sit on the balcony of a cruise liner and watch the ocean go by and read. So I'm going to show you a quick video. I actually trimmed it down to about 5 seconds, so you don't have to watch a lot of home video. So you might have to look back there. All right, so that's me walking out onto the balcony. Once you get, if you're on the top of the ship and you had no obstruction, you would look out and you'd see nothing but horizon all the way around. And you could see about 20 miles. So does that mean that I was in the center of the ocean with a 20-mile radius? Well, when I took this, we were actually off the coast of Venezuela. There's a 20-mile radius around it. You can see, I wasn't in the center of the ocean. I wasn't even in the center of the Caribbean. But you just can't see it. And that's what's happening with us. We don't really know how big the universe is because we don't know where we are with respect to anything. It's just that it's big. And if you want to do the math for how long, what's the distance of 46.5 billion light years, recall that a light year is the distance the light will travel in 1 year at the speed of 186,000 miles per second. So you do the math. That's how big it is. That's actually a number that is 273 sextillion miles. It doesn't really mean anything. And that's only what we can see. And of course, it's even larger. So that's looking outward. Let's look inward. Now, I thought it might be fun to, as we look inward, to look at our own human selves, to ask the question, why is life even possible on this earth? And these are not all of the coincidences, but these are a lot of the important ones. First of all, we are the perfect distance. We're in that Goldilocks zone from the sun. We're not too close or we burn up. We're not so far away that we freeze to death. The tilt of the earth is important because there's a lot of radiation coming from the sun, and some of it just bounces right off of us, we need that. The magnetic field of the earth has an iron core, and it creates a magnetic field. And that magnetic field is important because as cosmic radiation is coming in, it gets bounced off by the magnetic field. The location of the giant planets, like Jupiter and Saturn, it's important for them to be in our vicinity because they're so massive that as asteroids and other cosmic junk comes flying towards us, it gets caught by their gravity and doesn't end up hitting us. Chemical properties of water. I'm sure everybody's heard the old adage that water is the universal solvent. Everything in our cells, we're basically water. We're a big bag of water. But one unique thing about water, unlike all other liquids, is is that when water freezes, it becomes less dense. Most things, when they freeze, become more dense. So think about, we live here on the Niagara River. We see ice flowing down. Imagine what would happen if, as ice formed, it sunk, and then it froze up. Eventually, you'd have a frozen river, and all life that was living in there would now be frozen. But because it's less dense, it floats to the surface, and the fish are very happy down below. The properties of our atmosphere. It's like a big filter. When we think about it as being the means with which we breathe, which is true, but it's also a big filter, and it's designed to allow what I'll call the good radiation in, because we need it, and keep the bad radiation out. Photosynthesis. If it wasn't for plants and their ability to take solar energy and turn it into carbon-based food, we wouldn't be here either. But it also, this unique relationship between plants and animals, when we breathe in oxygen, and we breathe out carbon dioxide. Plants do the exact opposite. They breathe in carbon dioxide, and they breathe out oxygen. And if it wasn't for that oxygen they keep breathing out, we wouldn't be here, because we need it. That's where it all came from in our atmosphere. And then we have this flow of energy, which we'll talk about later, coming from the sun to the plants and ultimately to us. And then our location within the Milky Way. As I said earlier, we're kind of in that Goldilocks zone that allows us to see what we can see. Well, if you walk into any biochemistry, by the way, molecular biology is really like a merged field of biology and biochemistry. If you walk into any biochemistry laboratory, you'll see this chart. I don't expect you to see it, or read it, or even see much of anything on it. But what it is, it's all of the thousands of chemical reactions that are taking place right now in every one of your cells. You have no control over it. It's happening. So we'll take a little closer look. We'll go in a little closer. And again, it's still pretty complex. Let's take another closer look. So this is called the Krebs cycle. I'm not going to go through the chemistry of it, but it's the energy generator within your cells. Now, every one of those individual reactions, if you were to try to do that on a bench top, you need lots of energy. You need heat. You might need a big oven. But it's happening right now in our cells. How? There are proteins known as enzymes that allow this to take place. The enzymes pull the chemicals together. They reduce the energy required for the reactions to take place. And I've highlighted them in yellow, in red. But these are proteins. And these proteins are made in your cells constantly. That's happening right now. How does that happen? This molecule. My favorite molecule. This is DNA. And DNA, it's often referred to as the double helix. It's a molecule wrapped around itself. Let me show you another version of this. It looks almost like a spiral staircase. And you'll see these little letters in between, ATCG. We don't have little ATCGs in this. Those stand for chemicals. And you'll also notice that whenever you see an A on one of the strands, you'll see a T on the other. And whenever you see a G on one strand, you'll see a C on the other. And so when this molecule opens up to be replicated, it can use one strand as a template to recreate the other strand. But it also encodes your genetic code, the order of those letters. Now, again, we're not going to go through it, but those letters stand for adenine, thymine, guanine, and cytosine. That's what's really in between there. But molecular biologists like me, we don't need all that stuff. We just need the letters, because we can figure out what's going on once we know the letters. I just wanted to show you this, because remember I said the enzymes that are making those reactions take place, those are proteins. And proteins are synthesized in the cytoplasm of the cell, and it's directed by a molecule called, oops, it's funny, you wouldn't by a molecule called messenger RNA. And messenger RNA is coded for by DNA. DNA is the master molecule. So DNA is coding for the synthesis of RNA, RNA codes for the synthesis of protein, and proteins are the enzymes. Those reactions are taking place right now in all of your trillions of cells. Well, I like to think of DNA in the same way you think about a computer. A computer is hardware. It can do nothing until you put software in it. Once you put the software in it, it can do its thing. Well, the same holds true for a cell. The cell is hardware. It does lots of amazing things. You can think of it as a lot of little machines that are doing their thing, but it can't do anything without the instructions. So the software is the DNA. So that's how you can think of it. Turns out those building blocks that are called nucleotides, we have 6 billion of them in every one of our cells. And the order of them, those ATCGs, that's what makes you who you are. And if we were to do what we call DNA sequencing, where we can actually determine the sequence of those letters, we'd all be a little bit different, but for the most part, we're all human, so we all are pretty much the same, but we will differ here and there, otherwise we would all look the same. Well, in our laboratory, we sequence DNA, but we generate terabytes of data. I made the mistake one time. This is actually a photograph taken here in Buffalo at the Center of Excellence's supercomputer facility downtown Buffalo. That thing is churning away, generating data. And we have a site where we can log on and grab the data. And I inadvertently one day grabbed the entire file of many, many terabytes. Wasn't paying attention. I thought I downloaded a different file. I clicked on it. The blue screen to death is unfortunately, I was able to turn it off, turn it back on. But you need a supercomputer to analyze this data. This is a small gene. Most genes have about 15 to 25,000 of those little letters. This is the insulin gene, and it's only got roughly 4,000 of those letters. You'll notice that they're grouped in groups of 10, because people like me, you can't look at a stream of 4,000 letters. It doesn't make any sense. But at least when you see it in groups of 10, it'll help you understand when you're looking for certain particular patterns. And you also notice it's all lowercase, so that we can tell the difference between a G and a C, because it's a little easier when they're lowercase. Well, if you were to type out your genome, all 6 billion letters of it, you would get a stack of books. But I know this gives you no frame of reference. Here's your frame of reference. That's in every one of your cells. There's about 300 to 400 gigabytes of data in every cell. So with that, let's look at this scripture. And if you don't walk out of here feeling you're fearfully and wonderfully made, there's something wrong. Every one of us started out as this microscopic cell. This is a fertilized egg. And what you're seeing inside that egg, this is called the pronucleus. This came from the mother. It's got 3 billion nucleotides. And that's the pronucleus from the father, the other 3 billion. When they come together, you'll have 6 billion, and you'll have about 20. We don't even know how many genes. The order of those genes, nucleotides or bases or letters, makes up the individual genes. We've got somewhere between 25 and 30,000 genes in every one of our cells. Well, magically, after 9 months, that turns into that. And that was a dilemma for a lot of people because of the way cell divisions take place. Because what happens is a cell divides, and you get 2 identical cells. They're the same as the one that they came from. See, now you have 2 cells that are the same as the first one. Goes through another round. Now you have 4 identical cells. And John, you might have, let me say something first. What you're going to see here, this is an actual fertilized egg. You see the 2 pronuclei. They are going to merge, and then the cells are going to divide. And this is sped up with time-lapse photography. And what you're seeing, every cell division, is about 22 hours. You're going to see it in a few seconds. And John will probably only show, I'm not going to show the whole thing. I'll tell you when to stop. Go ahead. So they're going to merge. And again, it's not that it's disappeared. It's out of the frame of view. There's the first cell division. 22 hours. And another 22 hours goes by. And now there's 4 cells. And then another 22 hours goes by. And then you'll have 8 cells. Let's just do this one last division and then cut it off. Okay? Here's where the dilemma comes in. Every cell division gives rise to an identical set of cells. All the cells have the same DNA. If we took the DNA from any one of your cells, let's take one person, I think I need probably words since I know your name. If we took skin cells or hair cells or any other cell, the DNA would be identical. But the cells are not. And the reason they're not is the proteins are not. But how did it happen? So how do you end up with a baby instead of a big ball of identical cells? What happened? And what happened, this is the field I've worked in for many years, it's called differentiation. And it's brought about by something we call gene regulation. You can think of genes like light switches, and they turn on and off when they're supposed to. Something is telling them when to turn on and off. Let me give you 2 examples. Let's pretend we just built a big house with 20 identical rooms. They all look like this. Every single one is identical. And in the ceiling, we have some LED lights. It can be made to be any color we want it to be. And I'm only going to show you 3 of those rooms, but remember, there's 20 of them. Not trillions of cells, but for simplicity. And when you walk in the door, there's a set of light switches. And if I flip the first light switch, all of a sudden that white room is a blue room. And I walk into the next room, I flip on the red switch, and it's a red room. And the next one, a yellow switch. And you can imagine if you had 25,000 different combinations, and they're not just like one on or one off, there's combinations that are on or off. And that's what gives rise to these vastly different cells. So here's another example. Let's say now we have 3 different cell types. And remember, we've got 25,000 genes. I'm only showing you 15. And those genes, and I'm saying cell type A is liver, B is kidney, C is spleen, and I'm saying that the genes can either be on or off. Green is on, red is off. So the first one, that's what's on, that's what's off. Second one, that's what's on, that's what's off. Third one, that's what's on, that's what's off. So there are a couple things you can see. One, the combinations are different. And 2, sometimes they're the same. Because we have genes in our cells that are performing what we call housekeeping functions. All cells have to do certain things. So those genes that do that or control that, they're on in all cells. But the things that make you different from one cell different from the other is what's happening. So what's happening is the DNA is all the same, but in some cases the DNA is off, so it's not making those messenger RNAs, or the DNA is on and it is making those messenger RNAs, and when those messenger RNAs make their way out into the cytoplasm, those proteins are made. Some of them are structural, some of them are enzymes. That's where all the variety comes from, and that's called gene regulation. Well, I like to take a look at what happens when man tries to duplicate what God does. So let's start here. That's a heart-lung machine. Think about what it's replacing. It's replacing about this much real estate. And that costs about $100,000. And it won't do a thing until you plug it in. I don't see any extension cords that anybody would be in here. So that's our lung machine. This is a kidney dialysis machine. What's it replacing? These two little marvelous organs in the small of our back. That costs about $30,000. I think I'm going to stand over here so it looks like the pointer works better. And like the heart lung, it won't do anything unless you plug it in. I'll give you one more example. What I think is probably the most amazing organ in the body. It's the human brain. It's actually a real brain, so if you don't like the picture, look away. People have asked the question, can you duplicate the computing power of the human brain? Our brain is capable of incredible multiplexing. Think about it right now. Everybody in the room is breathing, at least, and you haven't thought about it, at least until I've mentioned it. But in order for you to breathe, your brain has to tell your diaphragm to pull down to create a vacuum so air will rush in. And it has to tell you, your brain has to tell the diaphragm to come back up. But you're also listening to me, or I think you are. So you're processing that information, and you're hearing me, and you're seeing me. And have you ever watched a TV program where it's out of sync? It drives my wife crazy when it happens. That's not happening to you. You're putting the sound and the sight together. You're integrating it. You may be moving around in your seat. You may be scratching. Whatever you're doing, you are capable of many, many multiplexing. Not to mention, you're capable of thought, and you're capable of creating things, music, art, and you can remember things. My wife and I joke about the church we got married in. We can still remember the very unique smell. Not a bad smell, it was just unique. And I could pull it into my brain. And that was 48 years ago, so I can still remember. So, they said, let's start easy. Let's duplicate 1 second of brain computing power. And they actually succeeded. Except, it took them 40 minutes. And except, it wasn't done on a high-powered desktop computer. It was done on a Rheonix supercomputer that's got 83,000 processors in it. To duplicate 1 second of your brain computing power. And that supercomputer, it doesn't do anything once you plug it in. So, in reality, the Rheonix supercomputer is not equal to the human brain. The human brain far surpasses the capability. So, the students that are here, you can do a lot better than you're doing. And we all know about power. We live here in Western New York. We know what it takes to make power. Well, our cells are making power. It's the only way we can survive. And in order to do that, there's an organelle in the cell called the mitochondria, but in order to see it, you have to look through one of these guys. And these are really fun. This is an electron microscope, and you get to see really tiny things. And this is called an electron micrograph. And again, maybe if I stand close here. So here, this is the nucleus. Here's the cell. And these two M's, these are mitochondria. And depending on what kind of cell you either have 1 or up to maybe 10,000 mitochondria. Those are the energy producers. Those are the little factories that are in your body. And this is just another view, a close-up view of the mitochondria. So basically, this is not even biochemistry 101. This is like biochemistry 1. Food comes in, and energy comes out in the form of something called adenosine triphosphate, or ATP. So, to kind of wrap this up, think about it. We look outside into the cosmos of space, and then we look inside. If we didn't have the sun, we wouldn't be here, because the energy that comes from the sun ultimately is transformed by plants, by photosynthesis, to make carbon-based materials. We come along, and we either eat the plants, or we eat the animals that eat the plants. So, in reality, the energy energy that came from the sun makes its way to us through the plants. So where does this leave us? I think we are indeed artificially and wonderfully made. And I think when you look at the complexity of the physical universe and its order, I think it points out that the scripture is true. So in reality, everything we see, everything we can't see, was made by him. So with that, I will take questions either now, I don't know how we're doing. It said we'd be an hour, it's 8 o'clock.
That's great. Yeah, we would like to open up for questions.
Okay. And my only comment is that when you ask the questions, as I said, my field is molecular biology, it's not astrophysics, so hopefully you won't ask me questions.
And since we are recording this, what we can do so that everyone can hear the question, I will go to the person, and you can just speak into my remote mic so that we can hear the question. Would you like to go first? On the spot. Fastball punch.
Well, plus we have the reception after, I guess.
Yes, there's a reception after.
People are more comfortable.
Sure.
The age of the earth, what is your
What
opinion?
do I think? So I was trying to keep all that, I'm like a politician that tries not to answer. I'm an older person, but I also think that God can do whatever he wants. I'm an older person. It doesn't mean that I look down on a younger person, because they might be right. But I just think we're in the billions of years. That's what I think.
Okay, so you're an older person.
Oh.
So I guess my question would be, when God created everything, he said it was very good. Was it not? And so if it was very good and you're an older person, then that means death and dying and cannibalism and all that nasty stuff happened before man was made. And so if it happened before man was made, then how do you explain it? Because God said that we're all under the curse because of what Adam and Eve did, and you're putting death and destruction before Adam and Eve.
That is actually the reason why I say I don't even think about it.
Well, there are things like creationministries.com, which is a young earth. There are lots of PhDs on there that I think the mistake that we as scientists, and I put myself in that category, do is that we don't separate operational science. I can boil water, and I know that it boils at 212 degrees because I can do an experiment that says that it boils at 212 degrees, versus historical science and what they call evolution, right? So you're looking at the same facts, but you are extrapolating backwards. And if you look at somebody like Lyell, he distinctly said the reason that he came up with old earth is because he wanted to separate Moses and the scriptures from science. I believe that they're both synonymous, because science is always self-correcting itself, always. So as you can tell, I am a young earth person. I believe Genesis means what it says and says what it means.
And I respect that. As I said, I think that we'll find out that when all is said and done, science and scripture will be compatible. I think, and I'm not taking sides. I'm not saying the science people are right or wrong, or the literal Genesis people are right or wrong. I think that in the end we'll see that God did it all. And, sometimes I think about like the debates that people have about the rapture. Is it pre-millennium, post-millennium, mid-millennium? What I think isn't going to change what it is. It is what it is. So in this case, it's not that I'm trying to escape the controversy. I just feel that the physical universe is so complex that I cannot subtract God from it. And to me, that's the most important thing. To me, it may not be to you.
No, I just think that when you're going against somebody who is an atheist, you, in your position you're taking, are very hard pressed to make the logical argument that I just made. That if you're trying, why do we need a savior? If death and dying occurred before the fall of Adam and Eve, then you're going back and saying, well, then Adam and Eve there was not really true Adam and Eve. And the entire gospel actually hinges on that. And that's where you get Genesis 3, where they are talking about the coming of a savior and why we need it. So my argument's actually much more logical than yours. Not mine, the Bible's argument.
What field of science would you encourage our young children who have an interest in science and love the Lord? Is there like a certain field you would encourage them as Christians to go into? And also, how can they protect their hearts in this field?
I guess I'm a little prejudiced in molecular biology, but I think any of the sciences, truly, you are correct that they will be met with challenges. We have 4 adult children, we have 5 grandchildren, and 3 of our children went through the public school systems on Grand Island, and our 4th one next would be homeschooled. So we've had a taste of kind of both worlds. And I think that what's being taught, the only thing I don't like about the way evolution is taught is fact rather than a theory. And from a Christian standpoint, I think it also brings up a lot of other issues. For example, evolution does not talk about the transformation of one thing, one person to another person. It's a population that changes. So all of a sudden, if you have a population, where does Adam and Eve come into play? They're a unique pair, not a population. So I think those kinds of issues have to be addressed. So as far as protecting their hearts, I think you have to do it in your home, I think. As far as the fields, in the field of, my field, it is such a rapidly growing field, but it's filled with all kinds of ethical issues, incredible ethical issues. You may or may not have heard of technology that can be used to modify genes, and is that acceptable? And is it acceptable if you're talking about a child that has a disease like hemophilia or sickle cell anemia or some other thing that it is actually due to one mistake in one of the letters in the genetic code, and if you could correct it, would you? Then the next question is, would you make changes that will impact that person's children? Because if we start messing around with genes, we don't know what we'll do 1, 2, or 3 generations from now. So it's getting more and more complex. I like the field. It's interesting. It's exciting. Fortunately for me, I've never had to deal with those ethical dilemmas because I don't work in those specific areas.
Pertaining to cloning,
Yes.
I'm not sure, did I read once that like when they make it's like a sheep,
Yes.
doesn't live as long or something?
Yeah, that's the first, Dolly was the first, the cow that was cloned. And, theoretically, you can take the nucleus out of, like one of us, and plant it into a female egg, that you remove the nucleus. And you'd have to reprogram the genes to go back to their first naive state and let them go through all those turning on and off of genes. So theoretically, you could do that. And people talk about doing that. Now, in the United States, it's not legal. You can't. The National Institutes of Health funds all this stuff. In fact, I've gotten lots of grant money, and in our grants, we have to state that we will not do that kind of work. They just won't fund it. But there probably are places around the world, and I know there are places around the world that are trying to do things like that. And I think it's a really slippery slope.
But why don't the sheep live as long as the first one? Just because that's the perfect grass?
It's just that, sometimes scientists think they know more than they do. And I think they just don't have the full picture. And I think it's going to be a while.
Well, how does that pertain, like, I hear they're making organs. Is that true?
Yeah, yes. There are people that are growing organs. And in that case, I guess I'm not so troubled by the ethical implications of that because they're trying to repair an organ and give you, instead of give you a pancreas because you've got diabetes. You need a new pancreas. I mean, that hasn't been done yet, but that's what they're working towards, that sort of work where you make an organ. Now, you have to make the organ, you don't make it in another person. You typically will do it in another animal, but it's a human organ. And that has been done, where human organs have been grown in laboratory animals.
I thought they were doing that with bladders, for example.
They may have, I'm not familiar.
One last question. I saw another presentation once where it talked about, I guess it's the DNA that talked about the messengers. You showed it takes the transporter, takes over here.
Yeah, right.
And that's why with any one of those components missing, it couldn't take place, and that's why it had to happen all at once, and that's why it's creation and not evolution.
Yeah, people keep coming up with new theories. Again, if you take God out of the equation, people come up with all kinds of theories. And, one of the ones that I always thought was kind of humorous, because it was a Nobel Prize winner. The structure of DNA was discovered by Francis Crick and, what am I trying to blank? James Watson. And Crick has postulated that Earth, the reason we have life on Earth is that we were seeded by aliens. And people have talked about a new form of a nucleic acid called a ribozyme. Now, a ribozyme is a form of RNA, but it can act as an enzyme. So it can self-replicate. So people are saying, well, maybe that's how life started, because we've got this RNA that somehow magically came together. And then, because it can self-replicate, it can make copies of itself, and then we can go one direction and make DNA, or go the other direction and make proteins. There's all kinds of theories that have been put out there, but none of them have held up any real.
There's this theory of jumping, because we don't have any real transitional life forms in the fossil record. The new theory is that somehow the different species kind of just jump from one form to another. Is that?
Yeah. I don't study evolutionary. It's ironic when I say that because molecular biology, I hate to admit it, essentially is the study of evolution in the terms of watching the way gene sequences play out across all species. But I don't deal with those issues. I just don't. Go.
Hi, thank you for your excellent presentation. I appreciate it so much. I have a background in biomedical pharmacology. Specifically, I work in alcohol and substance abuse with the Center of Excellence Downtown Medical Corridor. But I am neither an astrophysicist nor a geneticist, so I can't claim any specific knowledge. I am part of a science and faith think tank group of folks here that's been operating for a number of years in an apologetic setting. And the gentleman that heads that up here in Western New York actually is from Grand Island. And he has attended multiple...
Is it Dick?
Yes.
Oh, Dick is okay.
I called him earlier today, but I think he's busy. But he is extremely well versed, and he's done seminars at Eastern Hills Wesleyan and a number of churches around Western New York on origins and the information that we're discussing all here today. I would like to say to the folks that are, especially young Earth folks, that the evidence for old Earth is very strong, and none of us who hold that position is saying God could not do that in 6 24-hour periods. But the term known in Genesis does stand for other than a 24-hour period, meaning it could be whole epochs of time. The other thing is...
That's what Ross says.
Yes, Ross says this. And indeed, I on that, including pre-Adam and Eve death.
So when they use young,
Yes.
and they start saying 1, 2, 3, 4, 5, if you go back to the original Hebrew, they are talking about 24 hours, literal days. You guys are jumping through acrobatics to try to marry science with religion.
There is no Yom mentioned evening and morning time.
Well, I will refer you to creation ministry.
One of our challenges at the Christian community. So it's a very important question and one that has good presentations. So, but we just have a lot of time for a couple more questions. We're on this side, I guess. Huh?
Yeah, I don't know.
Nice model for the recording.
Yeah. Oh, for the recording. Do you have any knowledge of the Human Genome Project?
Yes.
I haven't heard much about that lately.
Well, Francis Collins, the picture I showed you, he was the head of the Human Genome Project before he became the director of the NIH. In 2000, he stood on the platform with President Clinton at the time and Craig Mentor, who was running a company. So there was actually competition between the government and a privately funded program, and they both basically tied at the end. But everyone agreed when it was all over, they really didn't have the complete genome, not yet, and we still don't. There are pieces missing that we don't understand. And to put it in perspective, it took 15 years and $3 billion to get the blueprint. So it wasn't even a complete genome. And that's what was announced by Bill Clinton. And now, when we do this kind of sequencing, it costs about $1,000, and we can do it in a few hours. So the technology has improved dramatically. But there are still pieces of the genome that we don't know what the sequences are. And the reason for that is there are these long stretches of what we call repetitive repeats, and they just appear over and over and over again. And when you try to, because when you sequence DNA, you literally chop it up, and then you analyze the individual pieces, and it's like a big jigsaw puzzle, and you have to see where they overlap, and that's what the supercomputers are doing. These pieces are so repetitive, people can't figure out where to put them, because they appear all over the place. And in the old days, they used to call it junk DNA, because it didn't do anything. I don't think there's any junk in the DNA. And most people now believe it has something to do with the regulatory processes, this turning on and off of genes. It's probably what it does, but nobody knows for sure. There's still a big black hole in terms of understanding.
There's one other question here.
Well, Doctor, I see in your bio that you're familiar and you're knowledgeable in the area of chemical carcinogenesis.
Oh, yeah.
Could you, in 50 words or less, describe what that is?
Chemical carcinogenesis. When I did my postdoctoral training, I did it at the MD Anderson Cancer Institute, and I worked in a laboratory that was looking at the chemical carcinogenesis. That's bringing about cancer by chemicals. And we were looking at chemicals that brought about a form of cancer called hepatocellular carcinoma, which is a liver cancer. And that's what we were doing. And many people believe that some of the forms of cancer that we see now didn't exist pre-industrial revolution. And now all of a sudden we have all these new chemicals that we didn't have them that are causing changes to DNA and causing these mutations that give rise to these cells that all of a sudden lose control. Because a normal adult cell will only divide so many times and then it'll just stop, which it should. But a malignant cell, it just keeps going. Because the genes that are controlling that function, the cellular replication, where the genes should be turned off, they're turned on. And all of a sudden they just keep going. So chemical carcinogenesis is trying to study that phenomenon.
Okay, we have one final multi-part question, and then we'll have refreshments, and you're free to, I'm sure Dr. Montagna would be available for other questions after your lecture.
I have a few questions from both areas, one astrophysics and one philosophy. Let's start first with your field. I've been taught in school many moons ago that ancient history. Do you have any view on that? Is that possible? Has it been done?
I have no experience whatsoever in knowledge of it. I would have thought, no, that doesn't happen. I would think it would happen. But I couldn't answer your question directly one way or the other. It's up to do a little reading myself. I don't know the answer.
So you don't know if it's being done?
I'm not aware of it.
An example would have been even that growing of the human inside of animal.
Yeah.
That would be close to mixing.
Well, not really, because what they're doing there, they actually start out with a scaffold. They're not starting from nothing. They start with a scaffold, materials that are man-made, and then cells are kind of coating it, and they allow it to grow, and then they do that inside of another animal to allow that organ to grow to whatever they want it to do. I mean, there's a lot, even 3D printing is being used today. I've got a friend that 3D prints ears. Now, they're not functional, but they look like an ear, and it's for people who lost their ears. Now, it's a little different setting. It's not a functional organ. But I'm not aware. That's not saying that nobody's doing it. I'm just not aware.
Now about astrophysics, just fundamental issues. Again, in school many years ago, I've been taught that light, the speed of light is one constant, and two is maximum speed in the universe. Is that still being taught?
Now that we know that Hubble is helping to show that the universe is expanding at ever-increasing speeds, and I've read that it's actually beginning to surpass the speed. I don't know how that happens. I'm not an astrophysicist, but I have read that some people believe that as this universe is expanding, it's expanding so fast it's beginning to exceed the speed of light. And when you think about Einstein's theory of relativity, the faster you go, time goes slower and slower and slower. So sometimes I think to myself, if you could get up past the speed of light, does time stop? The time stops. Is that eternity? I don't know. That's why I say theoretical physicists are like theologians when you read their work. So,
do you think that time is the property of matter? Meaning, time is that time the fourth dimension?
Like I said, I am not an astrophysicist, or I can't answer it.
Okay, thank you.
I wish I could, but I can't.
That was a great question. I couldn't even answer that question, but I do know what time it is. It's time to have some food. Thank you so much, Doctor. Good job, and we'll close in prayer. And Heavenly Father, again, we thank you for just the blessing of this evening to be together, and we thank you that you are the designer, the creator, the sustainer, and the empowerer of all that is alive. And we thank you that we are headed towards eternity, and the reason why we're headed towards eternity for good in all your abundance is because of Jesus. So we pray that you would continue to help us grow in our faith, strengthen our knowledge of your creation, and our knowledge of your scriptures, so that we can always be ready to give an offense for the hope that is within us to all that would ask us, always doing it in an attitude of gentleness and reverence. We thank you, we ask it in Jesus' name. Amen.